I know, but like it's just a quiz, man. They're like the least points of the in the categories, you know. And it's as far as quizzes go, this one's pretty easy. It's like, can you do derivative? Can you take a derivative of something?
No.
Okay.
That's what they ask.
Yeah.
Can you write the number?
Yeah. That's where you're at right now?
Yeah.
All right. So today we're going to be talking about finding extrema. And I'm going to talk about 3 methods of doing this. And depending on what type of extrema you're looking at, you may choose a different method. So for local extrema, we're going to use what's called the first derivative test. And basically what the first derivative test says is when that first derivative changes from negative to positive, that will indicate to you that we have a local minimum. Hi, thank you. It's Nora's. And when that first derivative changes from positive to negative, then we're going to have a local maximum. So this criteria is one that I would expect that you memorize, right? Like no one's going to give this to you on an equation sheet or whatever. You have to memorize like when you're going to get the local minimum and local maximum. Is it positive to negative or negative to positive? Whatever way, man, you need to. Oops. The other technique you might use is the second derivative test. And that says when f prime of a is equal to 0 and f double prime of a is less than 0, then you have a local maximum. And when f prime of a is equal to 0 and f double prime of a is greater than 0, then we have a local minimum. The next one, or the next situation is if we want to find absolute extrema. To do this, we need to do a couple of things. We want to first start by use the first or second derivative test to find the local extrema. And then check the endpoints. The absolute extrema, this would be on a closed interval. I should say that. So we have to check the endpoints of that closed interval and the local extrema. And whichever one gives you the biggest output, that's the absolute maximum, and the smallest output would be the absolute minimum. But that's the gist of it. Those are the 3 tests that you might end up needing to use. From here on, we're just going to do some examples of using these things. Okay, so I'll start out and I'll kind of do a lot, and by the end I want to be doing very little because I want you guys to be telling me what to be doing. I know that's It is pretty cute, huh? You like that kangaroo?
A kangaroo. Right?
Are you sure it's not a wallaby?
The heck is a wallaby?
They look just like a kangaroo. They're like smaller though. Haven't you ever gone on the Outback walk at the Detroit Zoo?
No, but you don't have to drive. It's a drive-through zoo. That sounds so fun.
Okay. All right.
Can you do it with me, Mr. Boyd?
Totally.
You have a very good stop.
All right. So the first example says find the coordinates of the local maximum or minimum of the function. So because it's local, I know I'm just going to be doing the first or second derivative test. So I'm going to do it both ways here. Does it matter which one you use? Nah, man. So to do the first derivative test, we'll start by finding the first derivative of f of x. What is the first derivative of 2x squared minus 12x plus 15? You were not ready to take the quiz today.
4.
Keep going.
5. No.
4x6.
Someone said 4.
4x.
No.
Come on, you stupid thing.
Wow. That's kind of mean to say.
No, I was talking to my computer. Minus 12.
That's it.
You could write plus 0 if you want. You don't need to, though. Great. That's the first derivative. So if we need to check for where the first derivative changes from,
Did you no longer go?
it just fell. It's the magnet that popped off too, apparently, huh?
It won't stick anymore. I got it.
Thanks, Nora.
I'm such a good student.
Yeah. So for the first derivative test, we need to check for where the first derivative changes sign from negative to positive or positive to negative, right? When can that happen? Two places. One of them is where it crosses the x-axis. The other could be at a discontinuity, right? Let's look at the function 4x minus 12. Is there any discontinuity on that? No. How do you know? Yeah, it's a polynomial. Polynomials are continuous everywhere. There's no discontinuity. All I have to do is worry about where it's equal to 0. So when I solve that, we get 3. Everybody feel good there? So to decide whether this is a maximum or a minimum, I'm going to pick a value on either side of 3. And then I'll plug those into the derivative. When I plug 0 in, I get negative. When I plug 4 in, I'm going to get a positive. So that tells me I have it's a local minimum. The way to think about it is when the first derivative is negative, that means it's decreasing. When it's positive, it means it's increasing. So it's got to be a minimum, right? All right. But the problem says it wants the coordinates. So it wants like an x comma y. We don't have the y, right? How do we find that? We plug it back into the original function. Yes, sir. Is that plus 15? Yeah. So we got there 18 minus 36 plus 15. So that's going to be negative 3. So we have a local minimum at 3 comma negative 3. Feel good there? If I was going to do the second derivative test, again, I start the same way. I find the first derivative. And then I set it equal to 0 or find where it's undefined. Still get that or I still get x equals 3. Then I take the second derivative. What's the derivative of 4x minus 12? It's just 4. Since that's greater than 0, I know I have a local minimum. And then we just go ahead and plug 3 back in, just like we did before. So we have 3, -3 is a local min. Again, how do I remember that this is what the second derivative test is telling me? Remember, the second derivative is going to tell us about the concavity of the function. When the second derivative is positive, it's concave up. So it looks like that. And that looks like a minimum. That's how I remember it. What do you guys think? NBD? All right, let's do another one. I think, therefore I am. That's Descartes. All right. So this problem says find the x-coordinate. Notice it's asking for only the x-coordinate, so I don't have to plug anything back in afterwards. To find the local minima and maxima for the function. So again, since it's just asking for locals, just first or second derivative test. There's no add-on to it. So we'll do the first derivative test and the second derivative test. Does it matter which one I do in practice? Not for the kind of problems you guys are going to be doing. In all reality, are there problems where it's better suited to do one than the other? Sure. Will you encounter those in this class? No. All right. So first derivative test. What do I do first? Take the derivative. What do I get? Okay. What type of function is this? Okay, is it ever undefined? Nope. So I just need to set it equal to 0 and solve. How do I solve a quadratic equation equal to 0? You could use the quadratic formula, or what else could you do? You could factor. Does it matter which one you do? Nah. What part of this problem is going to make the factoring maybe a little hard? The leading coefficient there, because I'm just going to go ahead and do it as a quadratic formula problem more often than not when I see that. So negative b plus or minus b squared over minus 4ac all over 2a. So what do we get here? We have 8 plus or minus 64 plus 36, so that's 100 over 6. So 8 plus 10 is 18 over 6, or 8 minus 10 is negative 2 over 6. So we have x equals 3 or negative 1/3. So I'll now make my sign diagram. Pick some test values. And then plug those test values into my derivative. And again, I don't really care what the number is. All I really care about is the sign, right? So if I plug negative 1 into here, I'm going to have 3 plus 8 minus 3, so that's positive. If I plug 0 in, I'm going to have 0 minus 3. Well, that's negative. If I plug 4 in, I'm going to have 48 minus 32 minus 3. That's positive. So negative 1/3 is local max, got to say local, and 3 is local minimum. And that's enough because it doesn't ask us for the coordinate, it just asks us for the x coordinate. So far, so good? You guys feeling good? Yup. All right. Let's do another. All right. It says given h of t equals 4tq plus 3t squared minus 6t with domain negative 3 over 2 less than or equal to t less than or equal to 2. What's this going to be telling us? Is that we can find absolute extrema because it's on a closed interval. How do I know it's closed from that? Because of the or equal to signs. Yep, very good. Okay, part A says find all the coordinates of all local extrema and classify them as max or minimum. So that's just the first or second derivative test problem, right? Yep. But that's not how we're doing it. You know why? Because when I was sitting in your chair in 1998, did I have a graphing calculator to use?
Yeah.
Nope. I mean, they existed, but did I have one? No. What's up?
Mr. Boyle's not in this room, but I just have to ask something about calculator.
Okay, what's up? I'm sure I can help you.
If I use this for imaginary numbers, this I,
Uh-huh.
will it work?
Should, yeah.
Okay.
Like, didn't you do that here?
Yeah.
Okay,
Okay. That was it.
that's
I
it.
just didn't know if it would work or not.
Should,
Thank you.
yeah. Sure. Hey, just for communication purposes, I'm done doing both the first and second derivative tests now. I'm just going to choose one or the other.
What is that supposed to mean?
Well, the previous two problems, I've done it both ways, completely unnecessarily, just to show you how to do each one of them. But from here on out, I'm just going to pick one or the other to do it. This one, I'm going to do a first derivative test. So we'll start by doing the first derivative. I notice that this is continuous over its entire domain, so all I have to worry about is where it's equal to 0. I'll start by dividing both sides by 6 to make the problem a little bit neater. I notice that this is would be, if it's factorable, it'll be easy to factor even though there's a leading coefficient, because all I have to do is figure out which one is the plus and which one is the minus. Since that has to be a positive 1 in the middle, I know that the positive has to go with the 2t and the negative has to go with the 1t. So that'll do. So I get t equals 1/2 and t equals -1. I'm going to draw my sign diagram. I'll pick some values for t here. And now you might say, Mr. Kulik, why did you pick such a gross value of t? Why the fraction?
Yeah, why the fraction?
Oh, it's the domain.
I can't pick a number less than -3/2 because it would be outside of the domain. Now, if you didn't notice that, would it have been fine if you picked -2 or something? Yeah, it'll work just fine. But get in the habit of not doing that. In this case, it would have been fine. In other cases, maybe not. In addition, you should probably check to make sure both of these values are inside the domain. Now, I don't think that the IB would be so terrible as to do that. I wouldn't do that to you. But this textbook is so poorly edited, they might do it on accident. anyway, continuing on. H prime of, so I plug these into the first derivative. I'm going to use the factored form to plug these into because it makes life really easy. So I plug -3/2 and I get negative times another negative. It's positive. When I plug the 0 in, I'm going to get a negative times a positive. That's a negative. And when I plug the 1 in, I'm going to get a positive times a positive. That's a positive. So this guy is my local maximum, and this guy is my local minimum. That's my answer for part A. To do part B now, it says write down the coordinates of the absolute maximum and the absolute minimum. So to do this, I need to check two things. I need to check the endpoints. And then I need to check my local extrema. Okay, so far so good. Now, that's going to be a lot of stuff to plug into my calculator. I don't want to do that. Let me show you an easy way to do this on your calculator if you got to plug a bunch of stuff in over and over again. So what I'm going to do is I'm going to go to the y equals and I'm going to type in this h of t function. And then I'll exit back to the main screen, and I'm going to do the y1 command. So I'm just going to do y1 of, so I don't have to type this into the formula a bunch of times. So we had 225, 32, 5, and negative 1.75. So this guy is the absolute maximum because it's the biggest number. And this guy is the absolute minimum because it's the smallest number. So it asks for the coordinates. So the coordinate here would be 232 and then 1/2 negative 1.75. Everybody cool? Yeah, this is section 10.1.
Do you have any vacation plans for break?
No, do you?
Not really.
Yeah,
I'm just gonna throw a party maybe.
throw a party. Like a
My mom would never.
like a pajama party though, right? Just for your friends. A slumber party.
She's getting her stupid slip on the
All right. Next example. It says a toy rocket is launched upward into the air. Its vertical position, s meters above the ground at t seconds, is given by the function s of t equals yada, yada, yada. Part A, find the average velocity over the interval from 1 to 2 seconds. When you hear average and then of a rate, what does that mean? That means slope. So that's just going to be like s of 2 minus s of 1 over 2 minus 1, right? Guess what I'm not doing? I'm not doing that by hand. I'm going to use my calculator and kind of do the same thing. So I do that, I get 3. The next question asks for the instantaneous velocity at t equals 1. When you hear instantaneous of a rate, what are you thinking? The derivative. So it wants me to do that, right? Guess how I'm going to do this? I could do it by hand, but let's do it on the calculator so we can remind you guys that you can do all these derivatives at a point on your calculator. So math and then command 8. That's the n-derive command. And then we'll do it with respect to x. And I already typed in the equation for s of t into y1, right? So guess what I'm going to put here? y1. I'm not going to type it again. I could, but no thank you. So I get 8 meters per second. How's that feel? Okay, part C says find the maximum height reached by the toy rocket and the time at which this occurs. So what are they asking for here? Is this a local or an absolute? Yeah, I agree from the context. What's the problem though? If I'm looking for an absolute. We don't have something. But
It didn't give us any bound.
Yeah, it didn't give us the closed interval. So one of two things we could do.
No, that's a green light.
Well, you could set s of t equal to 0 because that'll indicate the domain of this function, right? Because the rocket's going to take off from 0 and then land again at 0. That'll give us the t's for that. Or, which feels like a lot of work, or we could do the following. This is what I'm going to do. So the derivative is this, right? That's a continuous function. It's never undefined, so all I have to do is set it equal to 0. So I get 18 over 10 or 9 over 5, right? If I do a quick little first derivative test on that, if I plug 1 in to s prime, I'm going to get a positive value. If I plug 2 in, I'm going to get a negative value. So that tells me this is a local max. Watch this cool stuff here. If I take the second derivative now and set, what do I get? I get negative 10, right? That's negative for all t. So that means that s is concave down for all t. That means that any maximum, or the highest local maximum, is also going to be the absolute maximum, right? So t equals 9/5 is the time. And then if I plug 9/5 into s, that'll give me the actual height. So again, I already typed in s into y1. Do you think I'm going to do it again? Heck no, I'm not going to do that by hand. I got this rocket going a measly 17.2 meters. That's not very high. Yeah. I feel like those rockets where the kids jump on the air pad and it shoots it up in the air can go that high.
Probably is.
Yeah. All right, I got two more examples and then we can be done. How's that sound? Yeah, I thought that would be okay.
Sounds like a plan, you know.
All right. Given that the derivative of f is yada yada yada, find the x-coordinates of all local extrema and identify them as maxima or minima. What do you notice about this problem here? Sam, are we going to be able to do this on our calculator? No, because they gave us the derivative, they didn't give us the original function.
Oh, that is the derivative.
Yeah.
That's evil.
So again, you could do this as a first or second derivative problem. I usually prefer the first derivative. I notice that first derivative is a polynomial and it's continuous everywhere, so all I have to do is set it equal to 0 and solve. To solve x squared minus x minus 6, let's factor that. How does that factor? Thank you.
You got this. Yeah, 3 is bigger than 2. That's how calculus works.
You're on one today, guys. So again, I go ahead and plug these back in. I get positive, I get negative, and then I get positive. So what do I have here? I have a local max and a local min.
Yeah.
Feel good there? Yeah, what's up, Holmes? If you reverse the derivative. Yeah. We're going to be talking about the going backwards process in chapter 11. Yeah, to undo a derivative, we take something called an integral.
Oh no.
And that's what we're going to be doing in chapter. With what you guys are doing, there's nothing to complain about.
That's what you want. It sounds like something a math teacher would say.
Nah. And I will tell you this, from an AP calculus student point of view, the derivative feels like the easier thing and the integral feels like the harder thing. In reality, the integral is always much harder than the derivative. Because,
Do you mean the other way around?
nope. Because you can write down any function, and after your AP calculus class, you know enough to take the derivative of it. I could write down a function that you cannot integrate,
That's what I was
even
saying.
if you have a graduate degree.
Sorry, that's what I was saying. I was thinking
Yeah.
the integral sounds horrible. It's not like,
Yeah, but in practice, in the AP classroom, it's usually easier than the derivative because you can't nest like a million rules on one problem and still expect an AP student to do it. All right,
lost my side.
that's okay. Last example, a fruit distributor has noticed that the weekly change in the price of apples can be modeled by the function PC is equal to yada, yada, yada. Oh, it has a sign in it, where PC is the change in price of a kilogram of apples, and X is the number of weeks since the start of the year. Probably, but do we know how to take the derivative of something with a sign in it? We don't know. I know, but you guys don't. But read the question carefully.
So we
So what's up? Okay. PC is the derivative of some price function. It's already given you the derivative. That's the tricky part. You had to read the question, understand the context, that it's giving you a rate function, right? The price change per week. That's a derivative of the price function with respect to weeks. So if I want to do this, find out when the price of apples is at a minimum, I'm just going to be taking P of or PC and setting it equal to 0, right? Doing a first derivative test. Do you think I'm going to solve this thing by hand?
Yes.
I don't want to do that.
Dang.
What am I going to do instead? Yeah, I'm just going to graph this, bad mama jamma. As a quick little aside, this has a sine or a cosine or whatever in it. What mode should my calculator be in?
Gradient.
Incorrect.
What?
IB class, it's always going to be in degrees. Yeah. So those of you going back and forth, Maria, especially you, this class is always in degrees. AP Calc's always in radians. Cool. All right. No, it's HL has calculus. More calculus than this in it. So again, X is the number of weeks. So I'm going to set that from 0 to 52. Why 52? There's 52 weeks in a year, right?
56.
No. Not in the years that we're doing. Maybe some planet's years has 52 weeks in it. That's okay. And then the Y is going to be the price change per kilograms of apples. Anybody go out and buy apples lately? Pound of apples, like $3. What do you think I figured the price fluctuation would be about 50 cents up or down. I don't know. That seemed reasonable to me. That's a hefty apple price.
Or a negative.
Yeah. Healthy apple discount then. All right, so this is my function. How many maxima do you see? 1. Which one is it? The first one or the second one? I see 2 places where it's equal to 0, correct?
Second.
This is the maximum because it's going from increasing to decreasing, right? The derivative is positive here and then negative there. This other one is the minimum because it's going from, the derivative is going from negative to positive. So all I need to do is find those values. So I'll do the 0 command. Let's find the first one. So I got 5 for the first one. Oops. Oh, you stupid thing. We got 5, and the other one's going to be 31. So if I draw my sign diagram, I notice that PC was greater than 0 here, less than 0 here, and greater than 0 here. I read that all from the graph, right? I didn't actually have to do any test values here. So this one is my local max, and this one is my local min.
And that just gave you both.
Which gives me both my answers, right? So A should be week 5, and B should be at week 31. What do you guys say? Yeah, not bad. So you guys should do from section 10.1, 1 through 15. Reminder here that for Sunday, the problem set is now going to be 9.1, 9.2, 9.3, and 9.4 because you kicked your can on the quiz, moved up. But here's the good news. When do you think I'm going to check for homework?
Never.
Yeah, I'm not going to, until we get back to school, I'm not checking anything. I'm on vacation too.
I'm on vacation too, I'll check.
This 10.1 homework wouldn't be due until the week after we return. Everybody cool? Okay. Hi, Jack. All right, I'm done talking. You guys feel good? You learned a lot today?
Yeah.
First and second derivative test masters
Yeah.
or future masters?
Yeah.